Coal, gas, nuclear, hydro, and wind all finish at the same place. A magnet spins inside a coil, and everything upstream of it, the boiler, the reactor, the dam, the rotor, exists only to keep that magnet turning. Each one needs something delivered first. Fuel to burn, water to fall, wind to blow, light to arrive. One method needs nothing delivered whatsoever. It works in complete darkness, inside a sealed box, underwater, and 10 years after you last touched it. It produces electricity the instant you squeeze it, and stops the instant you let go. The material is a crystal, and the output is a pulse of 15 to 25,000 volts, enough to break down open air and throw a spark. You have almost certainly used one today, if you lit a gas stove or a barbecue. The honest figure behind that spark is 1 to 3 millijoules. That number explains both what this technology can never do and why billions of these devices exist anyway. $15 puts one in your hand. Let us dive in. Coal, gas, nuclear, hydro, and wind all finish at the same place. A magnet spins inside a coil of wire, and that motion pushes electrons along it. Everything upstream of that moment, the boiler, the reactor core, the dam wall, the rotor, 100 meters in the air, exists for the single purpose of keeping the magnet turning. Change the fuel, and you change nothing about the electricity. You have only changed what pays for the rotation. Solar is the one large exception. A photovoltaic panel skips the mechanical stage entirely and converts light directly into current, with nothing moving anywhere in the device. Now look at what all of them have in common instead. Every one needs something delivered before it produces a single watt. Coal needs coal, dug out of the ground and carried to the plant. A dam needs rain that fell somewhere upstream weeks ago. A turbine needs wind that is blowing right now, at a useful speed, in a place you are allowed to build. A panel needs daylight arriving on its face. That dependency is the reason energy is complicated. It is why houses have grid connections, fuel tanks, propane deliveries, and roof arrays. It is why every conversation about power turns into a conversation about supply, storage, and weather. Take that requirement away, and the problem changes shape completely. There is a category of generator that needs nothing delivered to it at all. It works in total darkness. It works inside a sealed box, underwater, in a drawer, at the bottom of a tool bag. It works 10 years after you bought it, having received no maintenance, no charging, and no attention of any kind. It produces electricity in the instant you touch it, and stops in the instant you let go. I should be honest about the scope of that immediately, because it matters. What this makes is a pulse, not a supply. It is a burst of electricity lasting microseconds, and there is no version of it that hums along in the background powering your house. That limitation turns out to be far less important than it sounds. Press the button on a barbecue igniter, and you generate a bolt of electricity at roughly 20,000 volts. Set that against the numbers you already know. Household mains runs at 120 or 230. A car battery sits at 12. And it takes something in the region of 15,000 volts to jump a quarter inch of open air, which is why spark plugs and lightning are in the same conversation and wall sockets are not. Your thumb produces that. Not by pushing hard, and not for long. The mechanism is a spring that loads up, releases, and drives a small steel hammer into a piece of crystal. The strike lasts a fraction of a second. What comes out the other side is enough potential to tear open the air itself. The gap between the electrodes stops being an insulator, the air ionizes into a conductive path, and a spark crosses it. There is no cell in there. Nothing was charged beforehand. No wire leads anywhere, except from one face of that crystal to the other side of the gap. A rock got hit, and lightning came out. The obvious question is what happens inside it. Quartz is silicon and oxygen locked into a repeating three-dimensional lattice. The property that makes it valuable is something that lattice does not possess. Most crystals have what physicists call a center of symmetry. Pick any point in the structure, look in exactly opposite directions, and the arrangement of atoms matches both ways. In a crystal built like that, positive and negative charges sit balanced against each other. Compress it, and everything shifts together. Nothing changes electrically. Quartz has no such center. Its atoms are arranged in interlocking spirals, and nowhere in that structure does the view in one direction match the view in the opposite one. So when the lattice is compressed, the positive and negative charges inside it do not move by the same amount in the same direction. they shift out of balance with each other. That imbalance drives a surplus of charge to one face of the crystal and leaves a deficit on the opposite face. A surplus on one side and a deficit on the other is what a voltage is. It appears at the same moment the pressure does. No warm-up, no chemical reaction working its way through a solution, no rotor coming up to speed. The deformation and the voltage are the same event, and both disappear when you let go. The effect also runs in reverse. Apply a voltage across the crystal and the lattice physically distorts. Hold on to that one, because by the end of this video, it matters considerably more than the forward version does. Now the three numbers that describe what actually comes out, because they sit together oddly. The voltage is enormous, 15 to 25,000. The current is minute, nanoamps to microamps. And the total energy is 1 to 3 millijoules, delivered in a few microseconds. Those figures belong together for a specific electrical reason. The crystal behaves like a very small capacitor with a very high source impedance. Capacitance that small holds almost no charge at all, and impedance that high means very little can flow out of it. But the voltage across a capacitor is its charge divided by its capacitance. And when the capacitance is tiny, even a minuscule quantity of separated charge produces an enormous potential. The crystal is therefore not a powerful source, but a tense one, developing very high pressure behind an almost empty reservoir. That energy figure needs a comparison before it means anything. A phone battery holds roughly 54,000 joules. A piezo press delivers about 2 millijoules, which is 2/1000ths of a single joule. Divide one into the other, and charging a phone takes approximately 7 million presses. At 1 press per second, without stopping, that comes to around 312 days, which reads like a verdict against the whole idea, until you ask what the spark is actually for. Methane ignites at a minimum energy of about 0.28 millijoules. Propane needs roughly 0.25. A piezo igniter delivers between 1 and 3. 10 times what the job requires from a thumb with no battery for the working life of the device. In 1880, in a laboratory in Paris, two brothers, aged 21 and 25, demonstrated that squeezing a crystal produces electricity. Their equipment was tinfoil, glue, wire, magnets, and a jeweler's saw. Pierre and Jacques Curie had started somewhere else entirely. They were interested in piezoelectricity, an effect known for years, in which certain crystals develop an electrical charge when their temperature changes. The brothers wondered whether mechanical stress might do something similar. So they cut crystals, glued foil to the faces, wired them up, and squeezed. Quartz responded. So did tourmaline, and topaz, and Rochelle salt, and cane sugar. Every one of them produced a measurable charge on its surface under pressure, and the charge scaled with the force applied. They named it from the Greek word piezein, meaning to press. A year later, in 1881, the physicist Gabriel Lippmann worked through the thermodynamics and predicted that the effect must also run backwards, that applying an electric field to those same crystals ought to deform them physically. The Curies went to the bench and confirmed it. Squeeze them and they make voltage. Electrify them and they move. Now the part of the story that turned a curiosity into an instrument. In 1885, the brothers built a device and gave it the plainest possible name: piezoelectric quartz. A slice of quartz hung from above, with a plate attached below it, so that a known weight applied a known force and produced a known charge. It was calibrated. It was repeatable. Jacques Curie recommended it as the standard method for measuring very small electric charges, because nothing else at the time could reliably reach those magnitudes. 13 years later, Marie and Pierre Curie were working through tons of pitchblende, hunting for whatever inside it was, producing the faint radiation they had measured. The currents involved were minuscule, right at the edge of what any apparatus could detect. The instrument they used to measure them was Jacques' piezoelectric quartz. The crystal that lights a barbecue is the crystal that found radium. The first application at industrial scale came from a former student of Pierre's. In 1917, with the war on and submarines sinking shipping across the Atlantic, Paul Langevin built an ultrasonic detector by gluing thin quartz crystals between two steel plates. The assembly resonated at around 50 kilohertz. Lowered into the sea, Driven electrically, it pushed a pulse of ultrasound into the water and then listened for the echo coming back. Time the return, and you know the distance. The device was not perfected until after the fighting had ended, so it changed very little about that war. It changed a great deal about everything afterwards. Every sonar set, every depth sounder, and every medical ultrasound machine in the world traces directly back to a stack of quartz between two steel plates in a French laboratory. 37 years separate the brothers with their jeweler's saw from a submarine detector in the Atlantic. There are billions of piezoelectric generators in the world, and most people own several without ever using the word. Start with the obvious one. Every push-button gas igniter contains a crystal barbecues, kitchen stoves, gas fireplaces, camping burners, laboratory Bunsen setups. The mechanism has barely changed in decades because there is very little in it to improve. Spring, hammer, crystal, gap, one honest substitution worth knowing before you build anything. Most modern igniters do not contain quartz. They contain lead zirconate titanate, a manufactured ceramic that is a dramatically stronger piezoelectric than any natural crystal. Quartz survives in the applications where stability matters more than raw output, and I will come back to why. Then there is the sensing side, which is far larger than the igniter business. A piezo element pressed against a surface turns the smallest vibration into a voltage. That is a contact microphone, and it is a guitar pickup, and it is the knock sensor bolted to your engine block, listening for the sound of fuel detonating early. It is the pressure sensor in industrial equipment and the impact sensor in a car. And it is medical ultrasound, on the order of hundreds of millions of procedures every year, which is Langevin's submarine detector shrunk down and pointed at a patient instead of at the Atlantic. Then the third category, and this is the one sitting closest to you right now. Cut a quartz crystal to a precise size, and it has a precise natural frequency. Apply an alternating voltage to it, and the converse effect takes over. The crystal physically flexes, back and forth, millions of times a second, and it holds that rate with extraordinary consistency. That is a clock. There is a quartz crystal in your watch. There is one in your phone. There is at least one in every computer in the building, in your router, in your microwave, and in every radio transmitter within 100 miles. Now notice what almost none of that has to do with generating power. So why has nobody built a piezoelectric power station? The effect never went into the power business, and the reason is the number from earlier rather than anything hidden. 1 to 3 millijoules per press is a hard ceiling, and it does not move with better engineering. It is set by how far you can deform a crystal lattice before the crystal fractures, which is not very far at all. You can improve the material, and manufacturers did. Lead zirconate titanate outperforms natural quartz by a wide margin. What you cannot do is squeeze a solid, substantially harder than its own structure tolerates. Scaling out does not rescue it either. 100 crystals require 100 presses, and every one of those presses is somebody's arm doing work. Harvesting from footsteps, dance floors, and railway platforms has been tried repeatedly, and the projects keep quietly ending. Because a person walking across a tile deposits a few millijoules, and the installation costs thousands. Nothing was suppressed here. The Curies published the whole thing in 1880, and anybody could read it. There is a more convincing piece of evidence than any argument I could make, and it comes from an industry doing exactly this job commercially. You can buy wireless wall switches that need no wiring and no batteries, ever. Press the rocker, and the switch harvests enough energy from your finger to transmit a radio command. They are an established product, sold as a building automation standard, and they work precisely as advertised. They do not use piezo. Inside those modules is a miniature electrodynamic converter, a magnet, a coil, and a laminated core, closer in principle to a bicycle dynamo than to anything the Curies built. Given a completely free choice about how to turn one finger press into usable electricity, the engineers who make their living at it selected the magnet because it yields more energy per press. That settles the power question fairly comprehensively. Now turn the same property around and look at it as a measuring problem. The characteristic that makes this crystal useless as a generator is that it produces a very large voltage from a very small deformation. For anybody trying to charge something, that is a frustration. For anybody trying to detect something, it is the entire point. A vibration far too small to see, far too faint to hear, arriving at a crystal, comes out the other side as a voltage a circuit can read. Sensitivity was always worth more than watts. The world bought this crystal by the billion for what it can notice and how precisely it can count. $15 buys a piezo igniter, a bag of piezo discs, and enough wire to do 3 genuinely useful things with them. If you want the full build, the element choice, the protection circuit, and the harvesting layout, we put together a complete walkthrough covering everything in this video and more. The link is in the description below. Start with the demonstration, because it requires no circuit at all. Take a bare igniter, strip the 2 leads, and hold their ends a few millimeters apart. Press the button. That gap is now a working spark, and you have built nothing. There is no supporting hardware in the world that made that happen, and there is nothing you can unplug to stop it. For a few dollars, it is the clearest physical proof of the effect available to anybody. The second build is a knock and vibration sensor, and this is the one people actually keep. Take a piezo disc, the flat brass ones sold in bags of 10, and glue it face down against a surface. Run its 2 wires to a microcontroller input, through the protection network I will come to in a moment. That disc now reports a fingertip tap on the far side of a table. It detects a door opening. It hears a bearing beginning to roughen inside a machine. It picks up footsteps on a floor above it, and it draws no power whatsoever while nothing is happening, because there is nothing to power. The signal is generated by the event itself. A battery-powered sensor is always awake and always consuming. This one is asleep in the strictest possible sense until something touches it. The third build is a contact microphone. Same disc, taped to a guitar body, a wall, a water pipe, a beehive. Feed it to an amplifier, and you are listening to sound traveling through solid material rather than through air, which is a different world of noises and a genuinely absorbing thing to spend an evening on. Now, 5 rules. 1. That spark is an ignition source. It was engineered to light gas, and it performs that job around solvents, fuel vapor, and fine dust exactly as well as it does at a barbecue. Treat a bare igniter as you would a naked flame. 2. Protect whatever you connect it to. A piezo element can spike far beyond what a microcontroller input tolerates, and a sharp mechanical impact produces a much larger voltage than a gentle press. The output goes through a series resistor and a pair of clamping diodes to the supply rails. Skip that and you will destroy the chip, usually on the first hard tap. 3. Do not use it on people. 1 to 3 millijoules will not kill a healthy adult, which is why the internet is full of people finding this out for themselves. It hurts. It is not a toy. And anybody with a pacemaker or any implanted device should be nowhere near it. 4. Never cut or grind crystal dry. Silica dust causes permanent, irreversible lung damage. Of everything in this video, this is the only hazard that will genuinely take years off somebody's life, and it is entirely avoidable by working wet or not working at all. 5. Support the ceramic. A piezo disc is brittle, and one struck without a solid backing behind it shatters rather than generating. The mechanical design matters as much as the wiring. 5 things I held back, because they only matter once there is a crystal on the bench in front of you. The first is impedance, and it explains a problem almost everybody hits. A piezo element behaves electrically like a small capacitor with a very high source impedance. Connect it to a low impedance input, the microphone jack on a cheap amplifier, for instance, and that input drags the signal down and strips the low frequencies out of it as it goes. The result sounds thin, brittle, and tinny, and people conclude the element is poor quality. The element is fine. It is being loaded incorrectly. Put a high impedance buffer stage between the disc and whatever comes next, and the same element produces a full, warm signal with the base intact. 1 transistor or 1 op-amp transforms the result. The second is bonding, and it is counterintuitive. Output depends on strain, not on movement. A disc left free to flap around will travel a long way and generate very little, because it is moving as a whole rather than being deformed. Bond that same disc flat and firmly against a surface, so that when the surface flexes, the crystal has no choice but to flex with it, and the output climbs dramatically. The third is resonance. Every element has a natural frequency at which its response peaks sharply, and away from that peak it falls off. If you are chasing a particular vibration, a specific machine, a specific note, a specific impact, it is worth matching the element to that frequency rather than assuming all vibration is equally detectable. The fourth is what to do with the output if you actually want to keep it. Piezo output is a sharp alternating spike, positive as the crystal compresses and negative as it relaxes. That needs a bridge rectifier to make it one-directional, then a storage capacitor to catch it. A purpose-built energy harvesting chip will manage that whole cycle far more effectively than anything assembled by hand, because it handles the impedance matching and the storage threshold together. The fifth is material, and it closes a loop from earlier. Natural quartz is a comparatively weak piezoelectric. Lead zirconate titanate produces substantially more output from the same deformation, which is why igniters and sensors are built from the ceramic rather than the mineral. Quartz kept its place for a different property entirely. Its resonant frequency barely drifts as temperature changes, and in timekeeping, that stability is worth more than strength. A clock that runs fast in summer is useless regardless of how much signal it produces. Choose by the property you need. The strong crystal and the stable crystal are not the same crystal. This will not charge anything, and no amount of clever circuitry changes the energy in a single press. What comes out is a pulse. It needs a mechanical input every single time, and it delivers thousandths of a joule when it arrives. That figure does not improve with a better circuit, a larger crystal, or a more ingenious arrangement, because the limit sits inside the material rather than around it. So the crystal never became a power source, and it was never going to. What it became instead is the only generator that arrives complete. No fuel, no charging, no connection, no maintenance, no waiting. It sits in a drawer for a decade and works on the first press. And because it produces a very large voltage from a deformation far too small to see, it notices things that nothing else in an ordinary toolbox can notice. That combination is why there are billions of them. In lighters and stoves, bolted to engine blocks, inside wristwatches, inside hospitals, and hanging beneath ships. Two brothers in their 20s measured all of it in 1880 with tinfoil, glue, wire, and a jeweler's saw. The instrument they built from that discovery went on to help identify radium. If discovering the practical, unglamorous corners of engineering matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. Now go and count. Without buying a single thing, how many piezoelectric devices can you find in your own house? Give me the number and tell me the strangest one. I read every single comment.